All right, so this is a wonderful example of what we call an exponential function. So exponential function. Y equals A times B to the x. So it's called exponential because your variable is up here in the exponent. Okay, those are called exponential. Different from like x squared, where x was down on the bottom. X squared is called what kind of equation? Quadratic. That's what we studied in the last chapter, chapter 7. What we just saw with exponential functions is exponential functions grow very, very fast. If you start with a penny the first day, 2 cents the next day, 4 cents the next day, by the end of the month, you're making over $10 million a day. So in just 30 days, this has grown from a penny to over $10 million. They grow very, very, very fast. All right, we have a couple of rules with exponential functions. The first rule is A can't be 0. And the second rule is B has to be positive, but B can't be 1. All right, well, the first one's pretty easy. How come we want A to not be 0?
Because you make it 0.
0 times anything would be 0. Not a very interesting function.
What if the volume of the month would that be higher than 0 but negative? If it was negative,
If A was negative?
yeah.
A can be negative. What's going to happen if A is negative is all your values are going to be negative.
Right.
So A being negative, you could consider if the boss figured out how much money he had to pay you, he might add this A be negative 0.01 because he's spending money rather than paying money. So A can be negative. All right, how come B can't be 1?
Because then it's just 1 over the 7.
Is 1 to a power, and 1 to a power is 1, so this would just be Y equals A. That wouldn't be very interesting.
I mean, it will. It's only getting paid once.
What if it's 200 billion then?
That'd be interesting.
It would be pretty interesting.
Now, how come B has to be positive?
Because if it's
Well, what if I just had Y equals negative 4 to the x? What's wrong with that?
Well, if the x is 3, it's going to be a negative number, but 4 is not.
Okay, well that's okay though, isn't it? If x is 3, then y is negative 4 cubed, which is negative 64. I get a negative answer. That's okay for me. If x is 2, on the other hand, y is negative 4 squared, which is 16. That's okay. Sometimes, functions can sometimes be positive, sometimes be negative. That's
Would
okay.
it look like an exponential sine wave?
No, it's worse than that. What if x is a half? Y would be negative 4 to the 1/2. That's square root of negative 4, and you're right, we end up with imaginary numbers. So that's the real problem there. We don't like B to be a negative number because we end up with imaginary numbers. And that's no good. Watch out for those imaginary numbers. All right, so the first thing we're going to do in this section is we're going to look at graphs. Let's start with a fairly easy function. Graph y equals 2 to the x. Well, we really don't know much about this function at this point, so we would probably build a table. And we always plug in 0 because 0 is a nice easy number. We would probably plug in a couple of our favorite positive numbers. What's a couple of your favorite positive numbers?
7.
1 and 2 and 3. Let's start with some small ones that start easy. And then we'll plug in a couple of our favorite negative numbers. No, the 7's not negative. Negative 1, negative 2, and negative 3. All right. Let's start with 0. What's 2 to the 0? 2 to the 0 is not 0. Anything to the 0 power is 1. That was one of our rules. Except for 0, that's correct. 0 to the 0 is undefined. 2 to the 0 is 1. If I plug in 1, 2 to the 1 is 2. 2 squared is, and 2 cubed is 8. So plugging in those positive numbers was pretty easy. What about 2 to the negative 1?
That's 1/2.
That's 1/2. Remember, what do negative exponents do? Negative exponents give you fractions. That's 1/2.
1/4.
2 to the negative 2 is 1 over 2 squared, which is a fourth. And 2 to the negative 3 is 1 over 2 cubed, which is 1/8. Again, those negative exponents do not give you negative answers. Rather, negative exponents make fractions.
So y can never be 0.
So in this case, you're absolutely right. Y can never be 0. How come y can never be 0?
Any fraction is not any number. It's something.
No matter what number I plug in, I'm either going to end up with 2 to a power, which is eventually going to make it big. Or if I do a negative power, it's going to give me 1 over something, but it will be something. So it will be 1 over something. You're absolutely right. There's no way I can ever get y to be 0.
It's really close to 0.
It gets really, really close to 0, but never reaches it. And there's a name for that. Anybody know the
I
name?
used to.
Not infinity. Your love life? Your love life's getting really, really close to 0? That doesn't sound good. Close, but never there. Not appreciation. All right, well, let's draw the graph first, and then we'll talk about what that is. All right, so we have 0, 1.
Yeah.
We have
No,
1, 2. We have 2, 4, so it's growing really fast. Oops, 1, 2 should have been right here. 2, 4 should be there. And then we had negative 1, 1/2, negative 2, 1/4, negative 3, 1/8.
Oh, that one looks like it's touching the line.
It looks like it's touching the line, but it really isn't. And so we get a graph that looks like this. This kind of graph is called exponential growth.
Yeah.
That's what you hope your bank account looks like. That's right. You hope your bank account does that and grows really, really fast.
If you choose option number 2.
If you choose option number 2, it would. All right, so there's a name for this graph. It's getting really, really close to this line, but it never touches it. Anybody remember the name? No, not decay. Although in a second we're going to talk about exponential decay.
It's
But it's not called decay when it gets close to the line. All right.
looks like
Alright.
Hangman. Hangman. I want A.
A? E?
I want S. Assumption.
No. Huh?
Y. Asymptote.
Asymptote. That's correct.
What did I say?
Asymptote.
I said asymptote, which is, I mean, somewhat close to that.
So this line, y equals 0, would be called an asymptote of this graph. What an asymptote means is you have a line, the graph is getting really, really close to that line, but never actually touching it. That's what an asymptote. Alright, so how about y equals 1/3 of the x. Alright, well, same deal. I'm going to build myself a little table. I'm going to plug in 3 and 2 and 1 and 0 and -1 and -2 and -3. It would be a backward version of the graph. You're right. So what happens when we plug in 3? What's 1/3 cubed? 1/3 times 1/3 times 1/3, which is 1/27. How about 1/3 times 1/3? Multiply tops, multiply bottoms, 1/9. 1/3 to the 1? 1/3. 1/3 to the 0? Not undefined. 1. 1/3 to the -1? 3, because again, what does a negative exponent do? it flips it. So that becomes a 3 over 1, which is 3. 1/3 to the negative 2 is the same as 3 squared. Again, the negative sign simply flips the fraction. That's 9. And 1/3 to the negative 3 is 27. All right, so now we have a picture that looks like this. We have 0, 1 still. We have negative 1, 3. We have negative 2, 9, way up there. We have 1, 1/3, 2, 1/9, 3, 1/27, so on and so forth. It goes, you're right, it's a mirror image of what we had last time. Oops, that's supposed to be a nice smooth curve. Ignore,
At the end, it just
ignore the little Humpty Doo there.
that's where it gets really rough. It'll go.
And that's called exponential decay. When it's decreasing like that, it's called exponential decay. All right, so where in life do we see exponential growth? Anybody have any examples of where exponential growth happens? What's that?
Bitcoin. There you go.
Bitcoin? For a while it was exponential. It's not anymore. It's kind of crashed at this point.
It's not a crash. It's at like $4,000.
Yeah, but it's not exponential anymore. It's leveled off.
Ish.
What's that? Unchecked population. It tends to be in an exponential growth. So if you look at the human population over the last couple hundred years, it's followed this kind of exponential growth pattern. The national debt over the last few years has followed this kind of exponential growth pattern. That's correct. So why are both of those things a very bad thing?
Because we don't want more of them.
We don't want more people?
No. Get rid of all of them.
What's wrong with exponential growth with having more people?
Fewer resources.
Yeah, eventually we're going to run out of resources. So if our population and you can see with this, as you can see with this example that we did at the beginning, where we started with a penny a day and it doubled and so on and so forth, it got really big really fast. And that's what's happening with human population right now. It's getting really big really fast. And eventually we're going to run out of resources. So something's got to give.
For technology, we already passed the carrying.
Probably yes, mostly because of transportation. Yep. All right. How about exponential decay?
Value of a car.
Value of a car.
As soon as you pull it off the lot, it's just done.
Value of a car for a very short time. When you first buy a car, it does drop exponentially. It becomes pretty linear after that. And then actually for a while, if your car gets old enough, the value starts to go back up. It becomes an antique.
Yes.
So for a very short time, cars are exponential decay, but not for long. Radiation is where the most common exponential decay examples occur. Uranium's a good one. Probably the most common one is carbon-14. Anybody know what carbon-14 is used for? It's used for carbon dating. That's correct. Why do we use carbon-14?
Because it's really, you can figure out half-lives from it, and then
Well, you can figure out half-lives from any radioactive element. Why carbon-14? What's special about carbon-14? No. Say that again?
Shows up organic.
Carbon, what's organic chemistry? Organic chemistry is the study of carbon. And the reason we study carbon is all life as we know it on this planet is carbon-based. No, all life, even jade. So the point is that everybody has carbon in them, and the half-life for carbon is pretty long. It's a little over 5,000 years. A little over 5,000 years, like 5,820 or something like that. I forget exactly. But that's why carbon dating is used. Now, carbon dating is no good for aging dinosaur bones, because dinosaur bones are millions of years old, and with a half-life of only 5,000 years, by the time we find a dinosaur bone, all the carbon, we can't measure it anymore, it's gone. And so for dinosaur bones, they do use other radioactive elements. I don't know exactly which ones they use. All right. The last thing we have in this. Let's say we have an exponential function, y equals b to the x, and it passes through the point 2 comma, those aren't good numbers, 2 comma 49. 2 comma 49. What's the equation of that function?
Y equals 7x.
Why does it have to be y equals 7 to the x?
Wait, why do that? So couldn't you just put the 2 in the x place and the 49 in the y place?
We put the 49 in the y place and the 2 in the x place. And so b has to be, we do square roots on both sides. B is 7. How come when we do square roots we only do the positive square root? How come I didn't do plus and minus?
Because who cares about b?
Oh, we do. How come I don't do plus and minus? How come my answer is only y equals 7 to the x? How about y equals negative 7 to the x? Because we don't want b to ever be a negative number because it gives us imaginary answers. That's correct.